Hi guys, a quick message or a quick lesson on what we call circular measure. The first thing that we need to remember is that an angle describes the amount and direction of the rotation. Okay, so if I'm talking about 120 degrees and it's positive, the positive angles are going to rotate counterclockwise. Okay, so counterclockwise we're going to be going from this bar to there. Okay, and it's 120 degrees. And if I was going to go the opposite direction, so negative 210, then I'll be starting at this bar and going around this way because it's negative, so I go clockwise for negative. Okay, so please remember negative angles rotate clockwise, so you're going down the way, and positive angles go up the way. Next thing that we need to consider is radian measure. So you've heard of radians now as a measure of angles. So what it is 1 radian is the angle at the center. So 1 radian is the angle at the center, so this angle here, of a circle produced by an arc that is equal in length to the radius. So if this is my radius here and this is my radius here, this arc length should be the same length as these radii. Okay? And then that length there gives me an angle in the center of the circle, and that angle is 1 radian. Okay? So the same rule applies if I had a smaller circle. Once I have a radius of that much and a radius of that much, then this length here, this arc length, has to be the same length as the radius. Then this angle here is 1 radian. Okay? Moving on. The radian measure of a central angle theta is obtained by dividing the arc length S by R. So the arc length we're referring to as S, it's often referred to as L also. And when you divide that by R, the radius, you end up with the radian measure of a central angle theta. Okay, so because the circumference of a circle is 2 pi r, so if I'm talking about the whole distance around a circle, it's 2 pi r. So I know that the circumference is 2 pi r. Okay, if I was talking about the radius of that circle, that's radius there, and if I was talking about the whole circumference, I would be talking about all this distance here, so essentially that would be this angle around here. Okay, and in order to find the angle I have to do 2 pi r, actually sorry, they're doing it for me up above, so therefore a full circle is 2 pi r divided by r, because that's our rule to find the angle. You do the length divided by r, so it's 2 pi r is our length, our circumference, divided by r, which gives you 2 pi. So that 2 pi now represents this angle here, which we know is 360. So therefore I can say that 2 pi is equal to 360 degrees. Okay, so 2 pi radian is equal to 360 degrees. And moreover, because 2 pi is equal to 3.28, so we've already recognized that pi is equal to 3.14 from doing area of a circle, etc. So 2 pi is approximately 6.28. So therefore there are just over 6 radius lengths in a full circle. So 6.28 means there's 6 holes and 0.28, so 6 whole radians. So again, if I look at this circle here, I know my radius, so each arc length needs to be a radius as well. So 1, 2, 3, 4, 5, 6, and then another little bit, the 0.28. Okay. So this just divulges a little bit more. So because the measure of an angle of one full rotation is 2 pi, because we take the length or the circumference S divided by R, so 2 pi r divided by r gives you 2 pi. So we know that a full circle is 2 pi. If I wanted to find half the revolution or half of a circle, I divide it by 2, which gives me pi radians. So therefore my pi radians is equal to 180 degrees. If I wanted to find a quarter of the revolution, I would be doing 2 pi divided by 4, which ends, when I simplify my 2 and my 4, I end up with pi over 2. Pi over 2 radians, which is equal to my 90 degrees. And then if I wanted to find 1/6 of the revolution, I would do 2 pi divided by 6, which leaves me with pi over 3 radians, and that gives me a value of 60 degrees. Okay, I can check them back by looking at the degrees that I already know. So it's 360 divided by 2, yeah, that works. 360 divided by 4, yeah, that works. And 360 divided by 6, yeah, that works. Okay. Moving on. These are other common angles. also given in radian measures. So 30 degrees is pi divided by 6, because if I have 180 divided by 6, I end up with 30. So essentially all these little sectors of my circle, there's 6 in 1/2, so there would be another 6 in this one, so it would be 2 pi divided by 12 essentially. So 2 pi divided by 12, if I broke my 2 pi up into 12 pieces, I would end up with pi over 6, and pi over 6 is 30 degrees, so it's 360 divided by 12. Same for this one, pi over 4, so it's 180 divided by 4, which is 45, 180 divided by 3 is 60, 180 divided by 2 is 90, etc. 180 is the pi, and 2 pi is 360. Another way to measure angles, the one that we're most familiar with, is in degrees, denoted by the symbol, the degree symbol. A measure of 1 degree is equivalent to a rotation of 1 out of 360, so there's 360 degrees in a circle, so 1 degree would be one of those 360ths. And to measure angles, it is convenient to mark degrees, so you can see here I'm going from 0 to 30, 45, 60, 90, and I can see it easily. So what we need to be able to apply from that information is the conversion between degrees and radians. So in order to do that, we have to use the basic relationship that pi radians is equal to 180. So we've already looked at that. Pi is equal to 180. So if I was to write pi over 180, I'm still only multiplying by 1. Okay? If I do 180 over pi radians, I'm still only multiplying by 1. So I'm not changing the value, I'm just changing what it looks like. So to convert from degrees to radians, I multiply by pi radians over 180, and to convert from radians to degrees, I multiply by 180 over pi radians. If you're ever confused which one to multiply by, when you see the examples now and what we're cross-cancelling, it'll make more sense. One other thing that you need to remember here, guys, when no units of angle measure are specified, so when there's no little degree symbol, when that's never implied, you presume that it's radians. Okay, so if you're told that theta is 2.4, you would imply that it's 2.4 radians. Okay, so again, 2.4 degrees is very, very small, so we rarely see angles like that. But if you ever see an angle without a unit, it's radians. So for this one here, it's 135 degrees, and I want to change it into radians. So if I look over here, I have to multiply it by pi radians over 180 degrees. Now the trick is, if you forget which way to do it, whether it's 180 divided by pi radians or pi radians divided by 180, the trick is the way you write it out. So I'm going to write out 135 degrees, and then I'm going to multiply that by pi radians over 180 degrees. And notice the way the degrees cancel. Okay, so because the degrees cancel, sorry, I went a little bit off there. Because the degrees cancel, I know that I have to divide by 180, so I should have known that my 180 was on the bottom. Okay, because this is degrees, so then I need to divide by 180 degrees. And when I do that, I get 135 over 180 pi radians, and 135 and 180 can be simplified to 3 over 4 pi radians. Okay, for 540, again I'm multiplying by pi radians over 180 degrees. The degrees cancel, and I get 540 and 180. They can also simplify to 3 over 1, i.e. 3 pi radians. Okay, that's it. It's pretty easy. The next one, this time I'm going from radians to degrees. So to do that, I need to multiply by 180 over pi radians. And again, you want that pi to cancel, so you're going to see that in a second. So it's minus 8 pi over 3 multiplied by 180 degrees over pi. The pi's cancel, leaving you with, so my pi's are going to cancel out. 3 goes into 3 once, and it goes into 180 60 times. 60 degrees, sorry, and then 8 times 60 is 480 degrees. Pretty simple. Okay, so you can do this, you should be able to do this without a calculator, by cross-cancelling. 5 pi over 6, I'm going to multiply my 5 pi over 6 by 180 degrees over pi. Again, my pi's cancel. 6 goes into 180 30 times, and 6 goes into 6 once. So 5 times 30 is 150 degrees. Okay, so really easy stuff to begin with. Equivalent angles in degrees and radians. So this is just something that you can have a reference to if you like. You'll become more familiar with this stuff as we go along. If I look here at my 30 degrees, that's pi over 6. If I was to go into the next 30 degrees, it would be another pi over 6, so it would be 2 pi over 6. Then 3 pi over 6, which can simplify to pi over 2. Then 4 pi over 6, which can simplify to 2 pi 3. 5 pi over 6, which is this one here. And 6 pi over 6, which can simplify to just pi. Okay? If I go jumping in 45s, pi over 4. So first 45 is pi over 4. Second one is 2 pi over 4, which is going to give me my pi over 2. The third pi over 4 is going to be 3 pi over 4, which is this one here. And then 4 pi over 4 again can be simplified to just pi. Okay, so you can actually jump in the common angles that we have. Okay, if I was to do my pi over 3, again, my first pi over 3 is 60 degrees. My second pi over 3 is going to take me here to this one, 2 pi over 3. And then my third pi over 3, 3 pi over 3 can be simplified to just pi. Okay, and it goes the same way into the second half of the circle as well. So exact values in trigonometry, so there's some common angles that we're actually supposed to know off by heart. So this whole table here, we will be expected to remember. Okay, so I'm going to show you where they come from, and then I'm going to give you a trick to remember them. So if I have a right angle triangle, and I let the other angles be 60 and 30, okay, and it's an equilateral triangle, because this is 60, and this top one is 60. So when I split it in two with a bisector, I get 30 and 30 on either side, and I know that these are right angles. Okay, so if my equilateral triangle was 2, 2, and 2, I can now say that this side length here is going to be 1 from there to there. Okay, and then if I'm trying to find this side over here, it's a short side and a right angle. And in order to do that, I'm going to use Pythagoras' theorem, but I'm going to subtract. So what I need to do is I need to do my 2 squared, which is 4, and my 1 squared is 1. And when I do 4 take 1, it's 3, and then I need to square root my answer. So my answer is the square root, oh, sorry, I need my pen, the square root of 3. So this side length here is the square root of 3. So I only need now this triangle here, the right angle triangle. And from that I can fill in different values in my table. So I have the 60 degree angle, so the sine of 60 degrees is going to be equal to, so looking at this, it's opposite over hypotenuse. So it's root 3, I hope I'm able to fit these in and write neatly, guys. So it's going to be root 3 over 2. And the cos of 60 is going to be the adjacent over the hypotenuse, so it's going to be 1 over 2. Okay, if I look at my 30 from this angle, my opposite is 1 and my hypotenuse is 2, so the sine of 30 is 1 over 2. 1 over 2, and the cos of 30 is going to be the adjacent, which is root 3, so it's root 3 over the hypotenuse, which is 2. Okay, so that's that first one. And then I can also if I wanted to, do my 90 degree angle from here. So it's so my opposite is 2 for the 90 degree angle, and my hypotenuse is also 2, so it's 2 over 2, which just gives me a 1. So the sine of 90 is 1, and the cos of 90 is actually 0 because it doesn't have an adjacent. Well, it does, it has either of these, but you can't choose, so 0 divided by 2 is just 0, so the cos of 90 is just 0. And then we can look at our second triangle here. Again, it's a right angle triangle, but this time it's an isosceles triangle. Okay, so it's got a side of 1 and the other side of 1, and then 1 squared is 1 plus 1 squared is 1, so the two of these together added is 2, so it's the square root of 2 to find the hypotenuse. And because it's an isosceles triangle, I know that both angles at the bottom are 45. So now I can use this triangle to create my 45 degrees. So the sine of 45 is opposite over hypotenuse, so it's 1. So it's 1 over root 2. And cos is also going to be the same, 1 over root 2. Okay? And we can find the tan by doing the exact same thing. So I can let you fill that up in your own time, because next thing I'm going to do is I'm going to show you a trick to how to find them without having to draw the triangles, and because that takes a lot of time. So I've got it. What we do is we lay out our hand and we label it 90 degrees, 60 degrees, 45 degrees, 30 degrees and 0 degrees. So each of the fingers has a common angle, okay, that was in our table before. So 0, 30, 45, 60, 90. And what we need to remember is that if I'm going from the 0 degrees, then I'm talking about the sine of the angle. And if I'm going from 90 degrees, I'm talking about the cosine of the angle. Now I'll explain this a little bit better. Okay, so what I'm using this for is I'm using it to find exact values much faster than drawing both of the right angle triangles and working out from the table of values. Okay, so if I want to find the cosine of 90 degrees, what I'm going to do is I'm going to look at this thumb, and what I want to do is I want to see how many angles are between this baseline here, 90, and the angle that I'm trying to find. So because I'm actually trying to find 90 degrees, there is no fingers between the 90 and this baseline. It's 0. So I can say that the cos of 90 degrees is equal to 0. Okay. If I wanted to find the sine of 90 degrees, I would have to work from the 0 baseline all the way back until I get to the 90 degrees. Okay, so how many fingers are between 0 and 90? There's 1, 2, 3, 4. And what I have to do every single time is I put all my angles over 2, and then I square root whatever I get as my answer, the number of fingers. Okay, so again, if I'm finding the sine of 90, I count from 0 all the way to that angle, and I end up with 1, 2, 3, 4 fingers. So the sine of 90, sorry guys, hands are getting in the way. The sine of 90 degrees is equal to the square root of 4 all over 2, which is equal to 2 over 2, which is equal to 1. So we know the sine of 90 is 1 degrees. Okay, let's try another one. So if I was to use, I'm just going to rub this line out this time. So if I was to try and find the 60 degree exact values, so the sine of 60 and the cosine of 60, so I'm going to use a different colour pen. So the cosine of 60 degrees, again, when I'm finding cosine, I have to start from 90 degrees up to the angle that I'm looking at, or the finger that I'm at. So from 90 to 60, there's only one finger, it's this one here. Okay, so I then have to rewrite it as the square root all over 2, that's a given, and it's the square root of 1 because there was one finger between the 90 and the 60, which is equal to 1 over 2, and the cosine of 60 degrees is a half. Okay, if I now look at the sine of 60 degrees, again I know that it's going to be the square root of something all over 2, and the number that I'm going to put in this box here is going to be the number of fingers. So I'm going to look at my fingers now between 0 and 60, and there's 3 of them, so I'm going to put that 3 in here. So the sine of 60 is the square root 3 over 2. Okay, and you can do the same for 45. Just rub out this red line. So if I look at 45, 45, I know my answer is going to be the square root of whatever the number is over 2. So if I'm going from the sine to the cosine of 45, I'm going from 90 to 45, so there's 2 fingers, so it will be the square root of 2 over 2. And if I was going for the sine of 45, it'll be 0 to 45, which is the square root of 2 over 2. Now just a little bit on that, the tan of the sine of 45, so I'm going to choose a different colour pen, I'm going to use black. So the sine of 45 degrees, when I do it from my finger method, I end up with the square root of 2 over 2. Okay, but on my previous page here, I got 1 over root 2. Now, the reason they're different is because if I was to try and rationalize my denominator, so it's 1 over root 2, in order to rationalize my denominator, I have to multiply by root 2 over 2, root 2 over root 2. Remember that root 2 over root 2 is just the equivalent of 1, so I'm only multiplying it by 1, so I'm not changing the value, I'm just changing what it looks like. And when I'm multiplying fractions, I times the tops and I times the bottoms. So if I do 1 times root 2, I end up with root 2, and if I do a root 2 times a root 2, I just end up with 2. Okay, so that's why they're a little bit different, but it's better actually to write it with a rational denominator. Okay, so what we've got here, this one here from the table, the 1 over root 2, it's better practice to actually write it as root 2 over 2. Okay. Yeah. So ask me in class if you have any questions on that, about this trick, because it's pretty handy. The last thing that we're going to look at during this lesson, is the unit circle. Okay, so if I have a circle that has a radius of 1, okay, so any point from the center to the circumference is a length of 1, so from the center to the circumference is 1, from the center to the circumference is 1, that's what I call a unit circle. And I can look straight away and I can say that this angle theta is giving me arms of x and y, basically. Okay, so the x squared plus the y squared gives me my 1 because it makes up a right angle triangle, and this is the hypotenuse. Okay, if I'm talking about this point here on my circle, I've travelled x horizontally and I've travelled y vertically. Okay, so that's why I'm given these yellow line x and red line y. Okay, but now I can also talk about my theta there. Okay, and we can use information that we already have. So I know that from my trigonometric ratios, the sine of theta in that right angle triangle there is going to be equal to opposite over hypotenuse, and the opposite is equal to y all over the hypotenuse, which is 1. Okay, so again I'm talking about theta here. The side opposite it is y and the hypotenuse is 1. If I wanted to say about the cosine of theta, the cos of theta, it's equal to adjacent over hypotenuse. The adjacent of the theta is this line here, the x line. The distance it's travelled is x over the hypotenuse, which is 1. So I can straight away say that sine theta is y and cos theta is equal to x. Okay, so if I wanted to write coordinates for this point here, I can say it's xy, which is cos theta sine theta. Okay, so it's xy is cos theta sine theta. So therefore cos theta is equal to x, sine theta is equal to y, or y is equal to sine theta, x is equal to cos theta. Okay, so you need to remember that. The other thing that we want to take from this example is that theta is our reference angle. Okay, and by reference angle we're talking about in the first quadrant. So theta is always going to be acute as a reference angle because it's in the first quadrant. So this angle here is always theta in the first quadrant. Okay, we can then use the other quadrants, so the second, third and fourth quadrants. We can also use the reference angle in there as well, because I can say that this from here to here, okay, is going to have similar distance in y and a similar distance in x. So the ratios are still going to be the same. So that's what I call theta in this quadrant. And if I was to do it in this quadrant down here, this would be my theta. And in this quadrant down here, this would be my theta. Okay, so this reference angle in the first quadrant can be used to find values in all the other quadrants. Okay, so this angle here can be used to find all the angles in this quadrant, all the angles in this quadrant, and all the angles in this quadrant. Okay. Notice here, if I'm talking about a positive angle, I'm going from the x-axis, the horizontal line, anti-clockwise back to here. Okay, so in order to find all of that angle there, I would be doing 180 minus the theta. So this one here is 180 minus my reference angle theta. Sorry, that didn't come out very clear. 180 minus my theta. Okay, so again I'm going to explain that. So this is my 180, this is my full sorry, it's half a circle, okay, so 180. But if I wanted to find this angle up as far as this line here, I would need to take away this theta. And this theta is the same as this theta because it's the reference angle. Okay, and that's for the second quadrant. If I wanted to find an angle in the third quadrant, I have to add it on. So it's 180 plus the theta, because I'm going to do the full circle. Sorry, not the full circle, a full half circle, so all the way to there, and then I'm going to go that little bit extra, which is also the equivalent of this theta here. Okay, and then for the last one, if I want to find something in the fourth quadrant, up as far as there, then I'm going to have my 360, and I'm going to minus this theta away. Okay, and the reference angle is it. So it's going to be, do this in red pen, 360 minus my theta. Okay, so that's for the second quadrant. This is for the third quadrant, and this one is for the fourth quadrant. Okay, and we're going to talk about that a little bit more in the next page. So all stations to central is how we remember it, and what I'm going to look at is the sine and cosines and tans in each quadrant. Briefly before I go on to that, guys, sorry, if I wanted to find the tan of the reference angle theta, I know that the tan is equal to O over A, and because I know my O is Y and my A is X, I can write it like that, and because I know Y is sine theta and X is now cosine theta, I know to find the tan I can divide sine theta by cos theta. Okay. So looking at my sine, cos and tan in all the different quadrants, if I'm talking about in the first quadrant, their x's and their y's are all positive in the first quadrant, so that means their cos and their sine are both going to be positive. And if both their sine and their cos are positive, when I divide sine by cos, I'm going to end up with my tan ratio, which are both going to be positive as well. Okay, so in first quadrant, they're all positive. Sine, cos and tan are all positive, like so. Okay, looking at the second quadrant, so I'm looking at this one here. My x's are on the negative axis, but my y's are on the positive. So again, cos is x and sine is y, so my sines are positive, but my coses are negative. And if my sine is positive and my cos is negative, positive divided by a negative is going to give me still a negative, so my tan is negative. So in this quadrant, my s is the only one that's positive, my sine. Okay, because my y's are positive. So in the second quadrant, I can say that sine, which we've already discussed is 180 minus the theta, which is the reference angle, is going to be the sine theta, cos theta, and tan theta. Only sine is positive, the cos and tan are both negative. Okay, so looking at the third quadrant, what does that t mean? That t means that tan is the only one that's positive. If I look at my x-axis, it's negative, my y-axis is also negative, so my cos is going to be negative and my sine is going to be negative, and a negative divided by a negative is going to give me a positive, so that's why tan is positive. So in the third quadrant, again, remember we're doing 180 plus the reference angle, so plus theta, so sine is negative, cos is negative, but tan will be positive. Okay, and in the last quadrant, I'm told that my y parts are negative, but my x parts are positive. So my y means that my sine is negative, but my cos is positive. And if my cos is positive, my y is negative, a negative divided by a cos to get my tan ratio is going to give me a negative, so therefore cos is the only one that's positive. So we can write that underneath. So the fourth quadrant tells us that cosine is the only one that's positive. Remember that 360 minus theta is just giving you any angle in the fourth quadrant. So the negative sine theta and the negative tan theta, but the cos is positive. Okay, so the way that we remember that is, remember that you're going anti-clockwise. So it's all stations to central. All stations to central. So A, they're all positive, sine's positive, tan's positive, cosine's positive. Okay, and that's it. So there's a lot to take in, and remember that these are in degrees, but it also has the same rules for radians.